Hello, good afternoon. It's what's today? Wednesday, October 28th. It's 1 p.m., 1 in the afternoon. We're continuing our easy lecture series. Name is Boris Jeremic. I'm in Davis, California. It's the first day that's actually really cold outside. It was 4 centigrade, 40 Fahrenheit. So fall is coming. I should say winter is coming. Today with me are Mr. Heshan Wang.
Hi, good morning, everyone.
Well, good afternoon, I guess it's, yeah.
Sorry.
And he's going to present today on analysis, probabilistic analysis or stochastic elastic wave propagation using Real-ESSI. Also, Dr. Yang is here.
Hello, everyone.
Good to see you guys. And Mr. Yusheng Yang is here too. Hello, Yusheng.
Hello, guys.
I will, I guess you can share your screen. So let's start by sharing your screen and going through presentation quickly. And then we're going to go actually and look in the input file. And while we do that, we're going to run the analysis for a short number of steps just to see how it goes. So yes, please
sure.
Go ahead and share your screen.
Okay.
We don't see actually. Okay, now.
Oh, so now you can see my screen.
No, now we see.
Yeah.
Okay, thank you. Go ahead. Yes, please.
So today we're going to continue our easy lecture series. Today we're going to show you an example on how do we use Real-ESSI to do stochastic elastic wave propagation. Actually, in this example, we're going to use some of the techniques we already presented in our previous several lectures. So this is our problem that we're going to solve today. So we're going to have a three layered site, with some uncertainties in the properties, material properties of the three layering. For example, the first layer, you can see the Young's modulus will be, have a mean value 120 megapascal and 20% of coefficient of variance. And then, so we're going to also considering some uncertain motion that are going to be input at the bedrock excitations to the bottom of the ground. And so we're going to do that by model such a site using a 10 element 10 shear beam element, and the element length is about 1 meters. And so as I mentioned before, for the uncertainties in the material properties, we're going to considering it as a marginally distributed log normal random field, and we're going to considering the correlation as exponential correlation with correlation length at 10 meters. And for the bedrock motions, we consider a motions from the seismic scenario, magnitude 7, distance 50 kilometers. And we're going to synthesize, a bunch of realizations of this time domain uncertain motions from the stochastic Fourier amplitude spectrum, the stochastic Fourier phase derivative. And so we're going to using 3 different uncertain materials, E1, E2, and E3. And the location information is assumed this material is at the center of the layer. For example, when we calculating the correlation structure, the material number 1 going to be located at the 8.5 meters as the representing point that we consider. And so actually,
I'm sorry. Can I just? So I don't see myself on the side. I can't wait. So this is 8.5 meters from bottom. So you're measuring from bottom. The layer is 10 meters deep, and so you're measuring from bottom. And but I want to point out one additional important thing, and that is that in this case, for this analysis, it is linear elastic, and next lecture we'll talk about elastoplastic. But even for linear elastic, well, you can say equivalent linear elastic, as is done in practice. This is taking into the account both uncertain material and uncertain motions. And we're going to get time domain solution, and this is going to be quite a bit better than what you get from frequency domain solutions that, like, for example, RVT or solutions like that. So anyway, go ahead.
Yes. Yeah. So basically, in our coordinate system, the orange is at the bottom, and this 8.5 meters, 5.5 meters, 2 meters is all respect to the bedrock, bedrock location. Yes. And so for the uncertain material parameters, we already have a lecture on how do we characterize them, and how do we do the polynomial chaos expansion. So basically here we represent this random field of the elastic modulus, using polynomial chaos of dimension 3 and order 2. And for the motions, we also have, yes.
Yeah, go back. So this is really important. A choice of the dimension and order is important, and one should, I mean, we'll provide these input parameters and these suggested orders and dimensions, but this is for this particular material. But it's always important to actually go back and check if your chosen dimension and order is close enough to what you actually want to model. So here you can see the check. You know, there's an exact. This is what is actually being modeled, and the polynomial chaos synthesized. And you see that it's actually very close. So this is good. This means that the PC dimension 3 and order 2 does really good job of mimicking or modeling this log normal distribution for material stiffness. Yes, thank you.
Yeah, that's true. Yeah. And similarly, you know, we have the uncertainties from the ground motion, and this is also, you know, we already showed those. This is the realizations. You know, the first 200 realizations we shown from the stochastic Fourier amplitude spectrum modeling, and then we check, you know, whether this ground motion is, you know, consistent with the GMPE in terms of the spectral acceleration. You know, whether they have the desirable amount of the variability, and also, you know, it's also very important to check, you know, whether your marginal distribution is Gaussian or not, because you know, we assuming the we model the ground motion at the Gaussian random process, and then we do the polynomial chaos for such a Gaussian random process. As you can see here, you know, this is the frequency distribution for the acceleration at 20 seconds. You know, they are very close to Gaussian distribution, and then, you know, then we're going to derive the statistics for such a Gaussian random process. We derive the mean, the standard deviation, the correlation for such a Gaussian random process. So once we have all those statistics, then we can go ahead to do the Hermite polynomial chaos and the Calculus logic expansion. Yeah, similarly as what the professor, you know, mentioned previously, it's very important to choose a proper proper number of the dimension and the order. So here for Gaussian distribution, usually generally the order 1 of the polynomial chaos is enough to capture all the mean and standard deviation. So it's very important to choose a proper number of the dimension of the random process. So we also talk about this in our previous, you know, lectures on how do we characterize the uncertain ground motion. So as you can see here, we're choosing 115 dimension, and you know, it's very easy to capture the marginal behavior, but you know, there are still a tiny bit difference, you know, in terms of the correlation. But we think this is already good enough, and you can see here, you know, if you choose a, you know, not enough number of the polynomial chaos dimension, for example, if you choose only 15 dimension, you know, you will have overestimated, you know, the correlation structure as compared to the, you know, exact correlation structure that we are characterizing from these realizations of the ground motions. And so once you have all those, you know, input, and you make sure, you know, you already properly characterize those inputs on certain motions and on certain material parameters, you can go ahead to do the stochastic wave propagation modeling using Real-ESSI. Yes.
So if I may just add, so as you might have seen, the modeling, probabilistic modeling of material requires many less stochastic dimensions, much smaller order, and and this is just the nature of the earthquake. Earthquakes go forward. I mean, if you look at the realizations, if you look at realizations, they're very uncertain, and so it takes quite a bit more terms in polynomial in stochastic space to characterize the motions. And this is actually really a research topic, but this is, it's important to make some choices and then go back and check and see if the choices are proper, if you can recover, if your modeling of your motions, just like it was the case for the material, modeling of motions is properly done with proper number of dimensions. Yes, go ahead.
Yeah, and then I will going to show you an example, like how do we really do this in the Real-ESSI. So now can you see my this is our
we see the input file. So what I would suggest is do you have it on the side? Can you run the example just so they see?
Yeah, I can.
You want to do it later, or maybe okay. So this is the input file, and Heshen is going to run the example, and it's going to run very fast because it's only a few hundred steps or so. And while he's running, make this window a little bigger.
Okay.
Make this window a little bigger. Maybe make a little font a little bigger if you can, just so we can see what's. Yeah, that's right. Okay, I guess, yeah, font is good enough. I guess there will be a lot to, yeah.
How do I increase the
you
font?
go to,
let me see, zoom in.
no, you're
This
gonna,
is large.
well, okay, fine, okay, good. So just run it and then we'll discuss. We'll look at the beginning of run and then we'll wait a few minutes. I mean, we'll go through the input file, look at the input file while this is running, and then we'll look at the end. So you run essentially easy -5. This is the name of the file, and it reports all sorts of statistics and so on. And so let it run and then go back to the window, the input file window, so we can.
So as the professor mentioned, that this is the file that we just running, so as we can go through, maybe step by step to how do we define all the uncertain material and uncertain motions, then how do we run the analysis. So first of all, you need to specify a model name as any a simulation that is done using Real-ESSI, and then this section is where we define the uncertain material parameters. As you remember that we're going to have 3 materials, which means we're going to have 3 marginal random variables. So here we have defined 3 random variables, 1, 2, 3, providing log normal distribution, their mean, their standard deviation, and also very important, their location information. Because this location, can you see this font is large enough?
Maybe
I can make it.
It's well, I guess let's see if you can make it a tiny bit bigger. I guess I can see it fine.
Okay. Yeah. Sure. Yeah. And and a very important information is you need to specify the location information of this random variable, because they're going to be used in computation of the correlation. In the correlation of this random variables, and then we define a random field, which is exponential correlation structure that will consist of these 3 random variables. And then you need to add these 3 random variables to this random field. And then you need to perform the Hermite polynomial chaos calculation law of expansion using the proper number of the dimension and the order. You can play with this parameter like dimension 3 and order 2. You can change the dimension from 3 to 4 and 5, and order also increase the order. And then once you done the polynomial chaos expansion for this random field, number 1, then you can use these random variables in this random field to define your uncertain elastic material. Elastic material. So here we have defined the 3 materials, and for 3 different layers. Here I specify the uncertain elastic modulus as the random variable, not a single value, but the random variables. Variable number 1, number 2, and number 3. And then here there's a very important part is you need to specify the units for this elastic modulus. Essentially here, we specify the unit to be megapascal. So for example, for material number 1, it's going to be a random variable number 1, which is the mean is 120 times this megapascal. Yeah. So once you define,
can I just add? I'm sorry for interrupting. Yeah. So the main point is that we define these random variables as just unitless variables.
Unitless.
But because in our case everything has units, we're dealing with physics, we're dealing with mechanics. We want to define those at some point, and so here we define them. Yes.
Yeah, that's true. Yeah. So then the second part, we're going to move forward to define the uncertain ground motion. So for the uncertain ground motion, again, we define a new random field called random field number 2. Now we specify the marginal distribution to be Gaussian, and then you need to specify the 3 important piece of information of this Gaussian random process: the marginal mean, marginal standard deviation, and correlation. As you can see here we are providing those information through 3 text file, and here the main text file. If you open it, I already prepared. So it's just a single column of the text file, and you can see here. So each line is the mean of that single time step. So here we have in total 1,599 time step, and our the total time steps. And similarly for the standard deviation, is also a single column. Is also a single column vector. And each column is specified. Each row of this column vector will specify the standard deviation for the Gaussian random process at that time. And the third one, you need to specify the correlation. Correlation would be a 2D array, right? So if you look at the file that we provided, it's going to be a 2D array, and and the dimension of this text file of this 2D array is going to be 1599 times 1599, which is the full correlation structure that you specify into the program. And so once you provide those information, then you can again perform the Hermite polynomial chaos Kaplan-Loeb expansion to this single random variable number 2. And here we're choosing dimension 115 and order 1. And here there's another very important step here is you need to specify the dimension for this 115 dimension because we have two different sources of the uncertainty now in the system. For the uncertain material, here we are using a dimension 3. That means the dimension we assign to this uncertain material going to be Casi1, Casi2, and Casi3, right? And here we have the second source of the uncertainty, which is the uncertain motion. And again, now if we just specify the dimension to be 115, actually the real dimension corresponding to this 1500 dimension should be starting from the Casi4 to Casi 153, right? So you need to specify additional information just to tell the system, how these uncertainties, different source of the uncertainties is aligned together with each other. So here, if you look at this information file, okay, so it contains 2 columns. The first column is just the local dimension, the ID of the local dimension. What do we mean by 115 dimension? And here, the second column is to specify what is the global dimension, in the total system, what is the global dimension ID corresponding to local dimension 1 and local dimension 2 and the local dimension 150. So in other words, in total, the system going to have a total dimension of the uncertainties of 153. And the uncertain motion will only consist from dimension 4 to 153. And so this is very important because this different source of the uncertainty we're going to be reflect in the computation of the triple product and double product. And so that is our next part, which is this part. So this part is you need to define the double product and or compute the triple product from this different basis of the random field, polynomial chaos basis of this random field. As I mentioned before in our lectures, this computation of the triple product can be quite, can take some time. Usually for this one, it might take several hours. So here, what we do is usually we just compute them for once, and then we will generate this computational result and save them into a HDF5. And we already talked about how this HDF5, the format, how it lay out. And then once we have this HDF5 pre-computed, then when we really do the analysis or do the modeling, we can directly load or add this triple product, double product from this HDF5. Yes, Professor.
So just to know, these are triple and double products of basis functions, and they don't change; they're always the same. And so you can pre-compute them and then use them many times over because they don't change. So this is really useful. I shouldn't say trick. This is a useful tool, useful way of doing analysis because those are not changing, and so you can just pre-compute them and save them in a file and then read them in. I mean, you can of course run you can compute them during the runtime.
Yes,
but it's not very efficient if you already know what those dimensions are going to be, and you can of course produce a number of these files and then play a little bit with those dimensions in orders, and then you just use those pre-computed ones for your analysis, which you're going to run. Yes, go ahead, please.
Yes, and then here you see we define a variable. The variable name called a number of response PC terms. So this is a very important variable that you're going to control how many number of the terms of the polynomial chaos you want to compute it in your response. So here, I mean, obviously, the more terms that you're requesting here, the more accurate result you're going to get. But here to save some time, so we just choose the 200 terms. Essentially, we're going to only compute the first leading 200 number of the 200 PC terms in the response. And once you have this random variables, you can go ahead to define your model. So in order to define the model, the first part you're going to define different nodes. So yes, Professor.
I'm sorry, before you go into model. So essentially, we do PC expansion for the material. We do PC expansion for the motions, and then for forces that come from motions or for applied loads down at the bottom. And then we also do PC expansion for the unknowns, for the degrees of freedom. And
yes.
And so it's always important to have some flexibility with these numbers to see how good your approximations are. So it's recommended that once you first run this model to try to get a little bit of more knowledge about sensitivity of your results to number of PC terms. And then once you get some knowledge about that, then you can just go ahead and run the simulation.
Yes.
Go ahead.
Yeah, that's true. Yeah. So once you determine this, how many number of terms that you want to compute for the response polynomial chaos, then you can define your model. So here, as you can see here, the definition of the node is a little bit different from our deterministic definition of adding a node to a FEM program. The additional part is this one, that you're going to specify the polynomial chaos terms equal to the number that you determined. And so now please remember that this 3 DOF, this is the physical DOF, and each of these single DOF, for example, UX, UI, UZ, going to be again expanded into 200 terms. So in total, you can see the total number of DOF for node number 1 would be 600 actually in total, right? Because it's 3 times 200 would be 600 in total. And so once you define this 11 nodes, then we have some we need to go ahead to define the element, which is the stochastic shear beam element, and we would define the area to be 1 meters per second. Sorry, 1 meter square, and the density to be 2,000 kilograms per cubic meters, and then we're going to define 3 different layers of the material, right? Of the element. So the first 4 elements would be the bottom layer. And here you need to specify the properly stochastic material, which is the material number 3, and also the triple product associated with this element. And obviously you need to provide the information about the cross section and mass density, and so on and so forth. So here we have first bottom layer would be 4 meters, the middle layer 3 meters, and top layer again 3 meters. And we assign different uncertain elastic material to different layers. And then once you define the element, then you can define many other stuff. For example, the viscous damping. So here we have been using the Rayleigh damping, with around 5% Rayleigh damping, and then we apply them to all these elements. And please note that so now the Rayleigh damping is actually because Rayleigh damping is actually a combination of the mass and stiffness matrix. So here the mass becomes an expanded mass matrix, and the stiffness matrix also become an expanded stochastic stiffness matrix. But the concept of the Rayleigh damping is still valid here. So and after the definition of the damping, we can also it's also very important to apply some boundary conditions. So as you can see here, we actually this beam is vertically and in y direction, right? It's in y direction. And so we're going to fix all the y direction, all the z direction DOFs. And here you need to use this stochastic, keyword. So if you use this keyword, the Real-ESSI will automatically not only fix the UI and UZ, but also fix the corresponding stochastic expanded DOF. So actually now you are fixing 400 DOFs associated with the node number 1. And so once you define all those damping boundary condition, then you can go ahead to move to the analysis stage. So you can start in a new loading stage. Here we call it a wave propagation loading stage, and then you can apply your load, which is a imposed random motions. And so here we specify, we apply the motions to the node number 1, which is the bottom of the model, and also we apply the motion in the x direction. So and here we specify the random process of these motions to be random field number 2, which is the ground motion random field that we already predefined.
So if I may just add quickly, so don't go this fast up and down. I'm getting dizzy. So the random motion, the random process, which in this case we call them, they're both random process and random field, was predefined up on top. So we just have to make connection here that the input random motions are such and such, and this is actually going to be the motions are going to be applied through penalty method. So you have to define the penalty stiffness, which should not be really too large, but depending on what's your stiffness of your system, so maybe 10 to 6 times more. So this is a good number because it's relative to the actual stiffness of your shear beam elements.
Yeah,
and,
that's true.
And then you have to define all the other components of the stochastic model, which is double product, number, and so on.
Yeah.
Right.
Yeah, and also, and this double product also you need to predefine, and we already load them through the HDF5. Yeah. So once you now you have the force, you have the material uncertain force. Now you need to define your solver. So here in Real-ESSI we have both a sequential and a parallel solver, and also you need to define for the dynamic analysis you need to define the Newmark integrator, and also the analysis algorithm. So here, because this problem is just a linear elastic problem, we don't need to do any convergence convergence control. And then once you define all those different analysis components, you can do your simulation. So here, actually, in total, as we mentioned before, this random process actually consists of 1,598 time steps. And here we're going to simulate only the first 100 time steps, and the time step would be 0.025 seconds. And of course, eventually you need to finish nicely by using this by keyword. And I think we already finished those simulation on the other hand. So you can go back and check all the output, all the message. So this is just showing you already defined those random arrival to the random field, and you perform 2 polynomial chaos expansion, right, for motion, for the ground process, and also you define the dimension for the ground motion process, and then you go to the simulation. We run the first 100 steps, and so as you can see here, the first 100 step will only be the 2.5 seconds because our time step is 0.025 seconds. And now, if you go to your folder, you will see there is a simulation HDF5 already been generated, and so this file actually will contain all the information of the result. So particularly, you might be interested in to looking at the to the nodes, and you can first of all you can check the number of DFs. So as you can see here, we have 11 nodes, and each node will have 600 DOFs. It's much larger than the deterministic FEM. Yeah. Yes, Professor.
But no. So yes, this is much larger, but it is still 1 to 2 to 3 orders of magnitude faster than doing Monte Carlo. You did some tests, right? And so yes, the system becomes much larger, but it's much more accurate and much more efficient.
Yes, and all the response polynomial chaos coefficient are computed and stored in this tool. For example, if you look at the generalized displacement dataset, so here if you can see here, this is a 2D array. So there are in total 100 columns, which means each column is going to be a system response coefficient corresponding to a single step. And for example, for each time step, it contains all the polynomial chaos coefficient for all the node in the model. As you can see here, so now actually we have in total 6,599 number of the degree of freedoms. And for example, the first 600 degree of freedom were corresponding to the response PC coefficient to node number 1, and then the node number 2 and node number 3. And yes, Professor.
You're not going to, of course, we just show how this looks like, but nobody's going to look at this. This is huge. There are ways to post-process this. There are scripts that are going to post-process this and give you the actual distributions at any location that you want. I mean, they're going to use these PC expanded terms of the degrees of freedom, and they're going to reconstruct the actual distributions. And you can get distribution. So PDFs, probability distribution functions. You can get CDFs. You can integrate those, get the cumulative distributions, fragilities, and so on.
Yes. And so here we have write a simple Python script to post process. So this is the file that we already run for the whole time loading history, just to show you the response. So once you just run this script, it will post the process. This PC coefficient to generate, for example, here the main here the main displacement and the standard deviation. The main standard for the time evolving displacement, and also the acceleration. Yes. So maybe I can. They already be
essentially, you can obtain a full statistics in each time step of the whole motion at any location. In this case, we're showing the top location.
Yes. Yeah, that's true. Yeah. So here, I think what I'm showing is the surface response, the top
Yes.
surface.
Yes.
Yes. So with that, I think I'm going to stop here, and
Okay.
we're going to provide those files, and you can download and try it out by yourself. Yes.
We can nicely package those. We can nicely package those files and produce a number of additional examples just for people to see how it goes and how is this done. This is new stuff, and this is this requires some thinking and a lot of examples for users to start using. But we're going to package it nicely and make it available. Anyway, thank you very much. So you can stop your screen sharing.
Yes.
I think we're going to be done for today. The next lecture is going to be very similar to this one, except we're actually going to go through non-linear material. This was equivalent linear, and we're actually going to go through non-linear material, inelastic, elastoplastic material, wave propagation, and this is going to be coming in next few days. So with that, I'll just stop recording.